Hello, everyone. I'm very glad to be here, and I appreciate Stephen and others to invite me to give a plenary talk about our recent work on third generation of vortex definition and identification methods. My name is CLiu from University of Texas at Arlington, Texas, USA. This is outlines of my talk. I will talk of first generation, second generation, new omega method, third generation, and Nutex omega method, Nutex choline method, and Nutex based new fluid kinematics, and some conclusions. We know vortex is omnipresent in universe everywhere, like tornado, hurricane, turbulence, galaxy. However, do we have any mathematical definition for vortex? No. So there are three generations of vortex definition. The first generation is given by Helmholtz in 1858. His definition is mainly about vorticity tubes, vorticity filaments, etc. And then we have second generation, which are currently very popular for the vortex identification, like delta, Q, number CI, number 2 method, etc. Today our report is about the third generation, including omega, Nutex omega, Nutex choline methods, dated from 2016. First, we talk about the first generation of vortex identification. It is vorticity-based definition given by Helmholtz in 1858. He defined vorticity tubes, filaments as a vortex. However, can vorticity represent vortex? In general, no. Which has been proved by many scientific and engineering applications. Vortex is not vorticity filament of vorticity tube. Look at this earlier fluid transition. The green one is vortex. This section is in the middle of the flat plate. The color represented the vorticity strength. Red means strong, large in vorticity. Green, smaller, and blue is small. We found the vortex happen in the place where the vorticity is rather small, not large, not in the red area, in the green area. Robinson actually in 1989 found vortex happens where the vorticity is rather weak. We look at this vortex isosurface and vorticity line. We will find the green tube isosurface of vortex. The lines are vorticity line. So the vorticity is larger outside the vortex. Inside the vortex is rather small. Not only in the magnitude, also the direction is different. This is the vorticity direction, and that's the vortex direction. They are totally different. Therefore, we cannot use vorticity to represent vortex. They are both vectors, but are totally different definition. We also look what is local rotation axis. We give the definition. A local fluid rotation axis is defined as a vector that can only have stretching or compression along its length. That means the vortex axis cannot rotate it. So this will give the dv. dv is the velocity increment. According to mathematics, it should be equal to gradient of vorticity dot r. R is the real eigenvector of the velocity gradient matrix. So this means dv only can along r. R is real eigenvector. Therefore, the real eigenvector is rotation axis. Well, this is nothing else but a Lutex. The Lutex, the definition is this real eigenvector of velocity gradient matrix. How about the vorticity? Well, that's the theorem. Vorticity is not local fluid rotation axis except for rigid rotation. It can be proved easily. Same thing along the vorticity vector. The dv is del v dot omega. Well, the gradient of velocity tensor can be decomposed to be A and B. We know B is antisymmetric. It's easily to prove is 0. R1, R2, R3 are eigenvector of A. So A R1 equal to lambda 1 R1, etc. We cannot take the lambda out. We cannot. Because lambda 1 is not equal to lambda 2, lambda 3. If we can take out unless lambda 1 equals 0, lambda 2 equals 0, and lambda 3 equal to lambda. In such a case, the fluid is pure rotation or rigid rotation. So in general, vorticity vector cannot be local rotation axis, where A and B are symmetric and antisymmetric submetrics. Since vorticity cannot be used to represent a vortex, there are quite a lot of vortex identification criteria developed in the past 4 decades. More popular ones are Q, delta, lambda 2, lambda CI, etc. Q, given by Hunt, 1988. Delta, Chong and Perry, 1990. Lambda 2, John and Hussein, 1995. Lambda CI, Zhu and Adrian, 1999. Well, we have problem with the second generation. First, they are all scalar, but the vortex is a vector. 2, physical meaning is not clear. What is Q? What is lambda 2, etc. 3, they are all contaminated in some degree by stretching or shearing. 4, they require a threshold. Threshold is not unique, but some kind of arbitrary and man-made. Different threshold will give different vortex structure. For instance, even for same DNS data on the late boundary layer transition, if we pick large threshold of lambda 2, we get a vortex breakdown. However, if we pick the small threshold, all the vortex are linked. There's no breakdown. Look at these figures. When lambda 2 is negative, 0.017, all this vortex breaks down. However, if we reduce lambda 2 to close to 0, for example, 0.003, all these vortex are linked. There is no vortex breakdown. If we look at this movie, so we change the threshold, we get a totally different vortex structure. That means the vortex structure is determined by the threshold. Doesn't make much sense, not make much sense. Therefore, we try to develop a new vortex identification method we call it omega. Omega use A and B. We know that A is the symmetric part, B is the antisymmetric part, or we call the vorticity submetrics. So omega equal to B normal square divided A normal square plus B normal square. This is pretty much like a relative stress. Here we have a small number of epsilon to avoid the division by 0 or very small number. We give some empirical formula for the epsilon. Well, the omega method has some advantages. First, is easy to perform. Second, is normalized from 0 to 1. Third, is insensitive. We pick omega equal to 0.52, which can work well. When we change from 0.52 to 0.6, even 0.7, the vortex structure change very little. Four, they're also capable to capture both strong and weak vortices simultaneously. So we receive many reports saying omega method is better than any other second generation of vortex identification methods. It is really for the relative strength of the vortex. Now I introduce the new definition, mutex, which is a mathematical definition of vortex. Mutex is a vector. The direction is the real eigenvector of the velocity gradient tensor. The magnitude is given by this formula, which is given by Dr. Wang and others in 2019. Dr. Wang is the chairman of this workshop. So, mutex is a quantified vector which opens a new gate for quantified vortex and turbulence research, not only for quantitative research. Here, the omega is vorticity, or is real eigenvector of velocity gradient tensor, and lambda ci, it is the imaginary part of the complex eigenvalue of the gradient of velocity tensor. Mutex is a mathematical definition of vortex. Because the mutex direction is really the vortex rotation axis. Well, here is the real eigenvector of del V. And the magnitude is exactly twice the angular speed of the fluid rigid rotation. Therefore, the mutex, it is mathematical definition for vortex. The major idea is to extract the rigid rotation from the velocity gradient tensor. Mutex was born in 2018 at the University of Texas at Arlington. People spent 160 years since Helmholtz, 1858, and finally found a mathematical definition for vortex. Since then, we have published 3 books about the mutex, one by Bentham, the other by Elsewhere, and the third one by Springer. And we have published more than 40 ACI papers, most of them are highest cited. The nutex and the nutex dynamics is very important since vortex exists everywhere in the universe. A mathematical definition of vortex or nutex will play a critical role in countless scientific research areas. There is almost no place without vortex in fluid dynamics. The nutex theory will be critical to research of hydrodynamics, aerodynamics, thermodynamics, oceanography, meteorology, metallurgy, civil engineering, astronomy, biology, etc. More important, it is critical to the turbulence research, turbulence generation, sustenance, modeling, and control. Since nutex is the vector definition for vortex, so it directly can be used to show the vortex, not the vorticity. No, that's the vorticity line. And the blue one, the green one are vortex isosurface. You can see the blue one are vorticity line, you see? They are not coincide. They are totally different directions. But look at the nutex. They have same direction as the vortex structure. So nutex can directly use to show the vortex structure. We know that velocity vector can show the streamline. Same thing, nutex vector can show the nutex line, nutex 2, but not Q, number 2, etc. They cannot get any line since they are scalar. Vorticity tube is not vortex, but the nutex tube is vortex. So we can see that the vorticity line is not vorticity line is not vortex, but nutex line is. I would like to recommend some new methods. The first one is the nutex omega method. The basic idea is nutex can represent the rigid angular speed without shear contamination. It's a pure rotation. The omega can capture both strong and weak vortices. So we just try to combine nutex and omega methods. How to do that? Well, this it is the Cauchy-Stokes decomposition for the principal velocity gradient. So we can do the Cauchy-Stokes. The originally omega method is b squared over b squared plus a squared, which really have a lot of shears. So for the modified nutex omega, just take these shears out. So we only use the rotation, maybe some stretching. So this formula can get the explicit formula because we know the definition of R, beta, and alpha. Finally, we get omega R tilde equal to this formula, we can see we take out the shares. However, we still have a small number of epsilon which needed to be adjusted. On the other hand, the omega R, we pick 0.52. It works very well for a lot of cases. If you adjust a little bit of the threshold, it's changing very minor. So we say that's insensitive to threshold change. And that's the graphics we use the modified mutex omega method for vortex structure in the bound nail transition. We can see they capture both weak and strong vortices. Yeah, like this is Tobin stitching wave of vortex. Well, this is the lambda vortex, and we are helping vortices, and until we get more and more complicated. Then I also would like to introduce the mutex choline definition and identification. The idea is that on any mutex isosurface, the dr is 0, the isosurface, but dl is dr dot dl, which means dl, the gradient of mutex, and dl, they are always orthogonal. The dot product is 0. However, the dl and the dl are not orthogonal only if dl no more in the isosurface, depending which is the rotation axis. Rotation axis is not isosurface. So we give the definition. What is rotation called? It is the line, the gradient of R cross product with the mutex is 0. That means the mutex gradient is parallel to mutex. The mutex choline is unique and threshold free. We don't need any threshold. How to do that? So we need to first calculate the gradient of mutex, the dl. Then we need to give definition of what I call. What I call is defined as a concentration of mutex gradient vector. Or we say that's a local maxima of the mutex. Then we need identification of what I call. Really in the method, we just located the local maxima. See? Then we just draw the mutex streamlines, the Nike streamline, to show what I call line. And look at this graphics. So if we draw the mutex gradient lines, they're all concentrated on some lines, which apparently is the rotation axis. Where we can see from this graphic, they always locate inside the isosurface because they are local maxima. We take them out, we get the vortex rotation choline. We can see from here, they always inside the mutex isosurface. Now we look at the mutex choline for boundary layer transition. all kind of vortex identification method depend on the thresholds. Different threshold will give different vortex structures. There's no proper or improper thresholds. No one knows. The Newton's core center is uniquely determined, which represents the vortex rotation center or axis. The Newton's core center lines give the unique and correct vortex structure with strength of vortex and are threshold free. So we look at some examples. First, we only need to find local maxima points. These local maximum points. These maximum points will give the Newton streamlines. That's Newton streamlines. With the strength, it's not threshold. The threshold give isosurface. So the red one means strong. The yellow one a little bit less. Green one smaller, and the blue one is very small. So we can find the Newton's core lines with different color to represent the different strengths. For the earlier transition, we have lambda vortex. We can take these core lines out. Well, we can also find it. This core lines is inside the isosurface. This little lid, this is only for the Newton's core line. This is Newton's core line and isosurface. This even later, we have a lot of vortices. We can find the vortex lines. Also, the vortex line will be inside of the isosurface. Again, this is just the core line and the isosurface from different angle from top. So the conclusion of the numerical results are the Newton's core line is the best vortex identification method for several reasons. First, the Newton core line is the only method that gives a unique vortex structure, which is threshold free, not the others. Second, they shows the strength of the vortex by the color. Third, they also show the direction of the vortex. We can look at these graphics and movies. We can see when you change the isosurface, you will see that the isosurface will be gone, but the water core line is never changed. Also, the Newton's core line also can show the rotation axis direction. We can find it. What is the rotation direction, but not for the Q or lambda to lambda Ci. No, but the Newton's core line. We can compare with the Q method. Well, we know Q method is threshold dependent. This is the smaller threshold, 0.005. You get a more structure. If you use large Q, you get a much less vortex structure. But anyway, for this area, we can find it, or that area, where we have a lot of vortex structures by Newton's core lines. but we find little when the threshold is small. We have nothing when the threshold is larger. But this structure never changed because they don't need a threshold. So this is unique. Apparently, a lot of vertex structure is lost if we use the CLiu method or other second generation of vertex identification method. For the other example, is about the same. You see? So we can, when the Q is small, we can get some structure. Yeah, but Q larger is not all structure. But look at the Newtek colline, a lot of structures, which Q and other second generation method cannot capture. Now we come back to the Cauchy-Stokes tensor decomposition, where we know that the velocity gradient tensor can be decomposed to be symmetric. They call it strain rate, and the B is they call the vorticity. A is symmetric and B is anti-symmetric. But people usually think B is for the rotation, but no, we cannot say that. So the problem with the Cauchy-Stokes decomposition is the vorticity cannot represent the fluid rotation. The vorticity tensor really is a mixture of vorticity shear and rigid rotation. For the strain rate tensor is symmetric, but they have a diagonal element. People think that that's the stretching, and long diagonal elements, they think the symmetric strain. Apparently, it's a mixture. It depends on the coordinates. So the CS decomposition is dependent on the coordinate system, and therefore it's not Gaussian invariant. So we introduce the principal coordinate system and get a principal matrix. Well, the tensor is unique, but the matrix is not unique. It depends on the coordinates. We call principal coordinates. That means the z direction is parallel to Newtek's, and xy direction are orthogonal to Newtek's. So in these coordinates, we get a principal matrix. Because the tensor is unique, the matrices are not unique. So we need to give a principal matrix. It's like this, or it's Newtek's. Lambda CR are real part of the velocity gradient tensor. And lambda R, it is the real eigenvalue of the velocity gradient tensor. And epsilon, Xi, and eta are shares. So in this principal coordinates, we get this we call principal matrix. It's very easy to decompose to be three parts. One is we call the rotation, the rigid rotation. The second is stretching or compression. The third one is shear. So we call R, SC, and S. Well, I need to explain that some people also have similar idea as our principal coordinates. However, in the principal coordinates, different points have different principal coordinates. So we cannot use, we must go back to the original XYZ coordinate system. Otherwise, we cannot do the derivatives, the integration, we cannot do. Because we already rotated the original coordinates, we must rotate them back by Q and P transform. In the principal coordinates, we have three parts, R, S, and SC. But now we come back, we get R tilde, S tilde, and SC tilde, representing rotation, shear, and stretching. Well, the rotation part is easy because this mutex is guiding invariant. The SC part, we also can find it. It is, I have two parts. One is a diagonal matrix. The other one is dominant by mutex. Of course, if for laminar, for example, laminar boundary layer, the mutex 0, so we just 0. S tilde is too long to show here. So if you're interested, you can see our paper, New Fluid Kinematics, published by Journal of Hydrodynamics. Here, we must emphasize the vorticity is not rotation. The vorticity must be decomposed two parts, mutex and shear, rotation part and non-rotation part. This is very easy to prove that because B is anti-symmetrical part can be decomposed rigid rotation and the shear. Therefore, so we can decompose the vorticity to be the two parts, R and S, or we call vorticity RS decomposition. Well, this decomposition is easy to do for different coordinates. Since R, S, and vorticity are Gaussian invariant, it's not related to coordinates. We look at this. That's the earlier fluid transition. In the lambda vortex, we pick one point to check what is vorticity, the red one, is large. What is the mutex, the rotation? It is small. So the major part of the vorticity are shear, not rotation. So vorticity is not a rotation. The magnitude is very different. Of course, the direction is totally different. We cannot say vorticity is flow rotation. No. We pick another point on the ring part of the helping vortex. We find a similar thing. The vorticity is large. The rotation is small. They are in different directions. So we also we called UTA RNR tensor decomposition. So the velocity gradient tensor can be decomposed in two parts, R and NR. R means rigid rotation, NR means no rotation. It is also easy to be done in any coordinates, in original coordinates, since the mutex, it is Gaussian invariant. It is not related to the coordinate. we need to list some core issues on the vortex definition identification. We know vortex is a natural phenomenon. Vorticity, of course, is a mathematical definition. So we try to find the vortex. There is some issues. One is what is absolute strength of the vortex? What is Nutex? Nutex is double, twice of the angular speed. Then what is relative strength of vortex? It's omega. Omega is relative strength. Then what is the local rotation axis? This is Nutex vector. Where is the vortex core center? That's some Nutex core lines. Then what is the size of vortex core? Well, this is still empirical. Now we pick 95% of the central Nutex stress. Where is the vortex boundary? Said Nutex greater than 0. Well, all these 6 questions can be answered by the third generation of the vortex identification method, not by first generation, not by second generation. Second generation can answer some questions about where is the vortex boundary roughly when the threshold is small. We have a table here to show what we can do by the third generation of vortex identification. We can find it for all these key issues. Only Nutex and Nutex omega can answer these questions. All the first order, second order cannot answer. They maybe can answer some questions about the vortex boundary when the threshold is very small. Finally, I give some conclusions. First, vorticity cannot be used to represent vortex. Second generation methods are all scalars, strongly threshold dependent and share contaminate. They are not either. 3. Nutex is the unique mathematical definition for fluid rotation of vortex. 4. The third generation can give answers on 6 key issues of vortex, including the vortex core. Number 5. Nutex and the third generation open a new era for quantified research on vortex science and turbulence, as vortex is the building blocks and the muscles of the turbulence. The Nutex based on vorticity Nutex shear decomposition. That's the vorticity RS decomposition and the UTA RNR tensor decomposition paved the foundation for the new fluid kinematics. So what is contributions by UTA team? So first, mathematical definition, Nutex. The direction, it is the real eigenvector of the velocity gradient tensor. And the magnitude we know is twice the angular speed of the local fluids motion, including existence, uniqueness, stability, etc. to principal coordinates and principal decomposition in both principal coordinates and original x, y, z coordinate system. UTA or NR, velocity gradient tensor decomposition. Or we say del V equal to R plus NR. Then there are several methods, mutex-based vortex core definition and identification. Really, the vortex concentration of the del R, not vorticity, that's the local maxima of mutex, which is unique and threshold-free. Then we also give the new omega method and modified mutex omega vortex identification methods. We further create the new fluid kinematics, where we are developing the new fluid dynamics. We also develop a number of fortune code for the mutex method and modify mutex omega method and omega method. And this code have been published in the UTA website. So you can download free from this website. This is some of our recent publications. As I said, we already published 3 books and over 40 SCI papers. Now, let me see some movies for the fluid transition on the boundary layer. This is from side view. We can see lambda vortex, hairpin vortex, ring generation, and they lose symmetric and become chaotic breakdown. Let me see next. This from the other angle from top. We can see the lambda vortex, hairpin vortex with ring generation and lose the symmetry, become chaotic, the vortex breakdown. Thank you for your patience. Any questions?